Swayam Prabha. Digital India. Educated India.
Welcome to lecture 10 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Model with Non-Spherical Disturbances. Now, so far we have considered the problem of estimation of parameters in the multiple linear regression models. So, we have developed OLS estimators and maximum likelihood estimators. For developing the least square procedure or least square estimators, we require certain assumptions on the model. Now, one of the basic assumptions is that the disturbances are identically independently distributed. Such disturbances are called spherical disturbances, and then it implies that different observations have common mean and the observations are mutually uncorrelated or independently distributed. Now, in many practical applications, this assumption is not satisfied. For example, suppose you are modeling the expenditure data. Say, suppose your y variable is expenditure of a family on food, and your independent variable x is the family income. Families belonging to the lower income group have their income constraints. So, obviously, on average their expenditure on food will be lower. Not only that, because of the income constraint, they do not have any choice, and then the variability of food expenditure for such families will also be low. On the other hand, the families belonging to the higher income group do not have such kind of constraints, such kind of income constraints. So, they have more choices. So, on average their expenditure on food will be at the higher side. Not only that, you may observe more variability on their expenditures on food. Further, if the observations are taken through time, then the disturbances may show some kind of autocorrelation structure. So, again the assumption of uncorrelated disturbances may not be satisfied. Then the focus of this lecture is how the properties of OLS estimator are affected if the assumption of spherical disturbances is not satisfied. How is it going to affect the unbiasedness or consistency or best linear unbiased estimator properties of the OLS estimator? And is there any alternative procedure to improve the properties of the OLS estimator in case the disturbances do not satisfy this particular assumption of IID disturbances? So, now we consider the model y equal to x beta plus u. Then the assumption of spherical disturbances is that expectation of u transpose is equal to sigma square u I n. So, here we are assuming that all the ui's have same variance sigma square u, and for I not equal to j, expectation of ui uj is equal to 0. Now, this assumption may be violated in many practical applications, and one of the example I have already discussed earlier. Now, you may observe different kind of situations in different practical applications. So, for example, sometimes you observe heteroscedastic disturbances. So, suppose variance of ui is different for different i's. So, it is not constant. Then we say that the disturbances are heteroscedastic. If all the variances are equal, this assumption is satisfied, then we say that the disturbances are homoscedastic, and if the variances are unequal, then we say that the disturbances are heteroscedastic. Then cross observation correlations. Sometimes you have expectation of ui uj not equal to 0 for I not equal to j. So, the observations are not uncorrelated. So, you observe cross observation correlations, and sometimes this assumption of spherical disturbances is violated because of cluster effects. So, suppose you are taking observations in groups, or observations are coming in groups, then the observations within group may have some sort of correlation, but the observations across groups are uncorrelated. So, this is clustering effect. If you take observations within a group, then those observations are correlated, but across the groups the observations are uncorrelated. Now, we consider the model with non-spherical disturbances. So, suppose the disturbances are non-spherical and expectation of u transpose is equal to v, or you may write it equal to sigma square u omega, where v or omega, these are positive definite symmetric matrices. So, V is actually the variance covariance matrix of U, the disturbances. So, in case omega is equal to identity matrix, then we have spherical disturbances, then the assumption of spherical disturbances is satisfied. We have expectation of u transpose equal to sigma square u I n. But if omega is not equal to identity matrix, then the assumption of spherical disturbances is not satisfied. Then for non-spherical disturbances, we refer to model as generalized linear model. Usually we prefer to write the covariance matrix in the form sigma square u omega. So, in this lecture I am going to use this notation for the variance covariance matrix of u instead of v. So, that if we set omega equal to I n, we get the classical model with expectation of u transpose equal to sigma square u I n. So, simply if we replace omega by I n, we get the classical multiple linear regression model. Now, we consider some special cases. So, first we consider the case of heteroscedasticity. The disturbances are said to be heteroscedastic when they have different variances. So, again suppose you have n observations and those n observations are divided into g groups, and there are ni observations in the ith group. So, that n is equal to summation I equal to 1 to g ni. Now, suppose we assume that the disturbance variance in different groups are different. So, the variance varies in different groups. The example which we have discussed earlier, the observations belonging to the lower income group have lower variability, lower values of sigma square in comparison to the observations belonging to the higher income group. So, different groups have different variability. Now, we write the model as say y 1, y 2, so on y g equal to x 1, x 2, x g beta plus u 1, u 2, u g. Here y I is of order n I cross 1, x I is of order n I cross k, and u I is of order n I cross 1 for all I equal to 1 to g. So, ultimately this vector y 1, y 2, y g is of order n cross 1, because n is equal to summation n I. Again each x I is of order n I cross k. So, ultimately this entire matrix is of order n cross k. Similarly, this vector of disturbances is of order n cross 1. Each of u I is a vector which is of order n I cross 1. Further, we assume that expectation of u I transpose is equal to sigma square u I n I, and for I not equal to I dash, expectation of u I dash transpose is equal to 0. Actually, this 0 is a matrix with all elements equal to 0. Now, suppose we write the model in the form y equal to x beta plus u, then expectation of u transpose is equal to v, and this v is equal to sigma 1 square I n 1, then here you have sigma 2 square I n 2 and so on, sigma g square I n g, and all other elements are equal to 0. Notice that u is equal to u 1, u 2, u g, and each of these u I is a vector of order n I cross 1. So, expectation of u transpose is equal to expectation of, here you have u 1 transpose, u 1 u 2 transpose, so on, u 1 u g transpose, u 2 u 1 transpose, u 2 u 2 transpose, so on, u 2 u g transpose, and so on. At last, we have u g u 1 transpose, u g u 2 transpose, and so on, u g transpose. And when we take expectation, then expectation of u 1 transpose is sigma 1 square I n 1, expectation of u 1 u 2 transpose is 0, and so on. So, finally, we obtain this matrix, expectation of u transpose is equal to this matrix. Now, the second example is autocorrelated disturbances. So, autocorrelation is usually observed for time series data, and the disturbances usually have common variance, but some kind of autocorrelation. So, the disturbances are autocorrelated. So, since we are taking observations through time, so I have slightly changed the subscript. So, instead of I have taken t here. Expectation of u t square is equal to sigma square u for all t equal to 1 to n, and expectation of u t plus I is equal to sigma square u rho I for all I greater than 0. Then expectation of u transpose is equal to sigma square u omega, where omega is the matrix with diagonal elements 1, and the off diagonal elements are, say, 1/2th element is rho 1, nth element is rho n minus 1, and so on. So, we get this variance covariance matrix, which is not of the form of sigma square u I n. Here you are not getting I n, and the problem is because of this autocorrelation structure. Now, we consider the special case of autocorrelated disturbances. Suppose u t follows an AR1 process, u t equal to rho u t minus 1 plus epsilon t. Here rho is the autoregressive coefficient and epsilon t's are IIT random errors, with expectation of epsilon t square is equal to sigma square epsilon, and expectation of epsilon t dash is equal to 0 for all t not equal to t dash. Then using the properties of AR1 process, one can easily verify that expectation of u t plus I is equal to sigma square u rho to the power I for all t equal to 1 to n. And then in this case, omega is equal to this matrix with diagonal elements 1, and off diagonal elements are rho square and so on, rho to the power n minus 1. Then here we have rho 1 and so on, rho to the power n minus 2 and so on. So, this omega is this matrix. Then some other examples of models with non-spherical disturbances are model with autoregressive conditional heteroscedastic or arc or generalized arc disturbances, or panel data models. In the panel data models we will discuss in one of the lectures. Then the models having spatial autocorrelation. Some of the models have spatial autocorrelation. So, instead of time series data you have spatial data, but sometimes even in spatial data you observe some sort of autocorrelation structure. Now, we investigate the finite sample properties of OLS estimator for generalized linear model. So, for the model with non-spherical disturbances, the OLS estimator B is unbiased. So, the property of unbiasedness still holds, there is no problem. The variance covariance matrix of B is expectation of B minus beta transpose equal to sigma square u x transpose x inverse x transpose omega x transpose x inverse. So, notice that this variance covariance matrix of B is different from the variance covariance matrix of B for the spherical disturbances. If omega is equal to identity matrix, then expectation of B minus beta transpose is equal to sigma square u x transpose x inverse. So, here we get a different expression for the variance covariance matrix of B. Then if U follows a normal distribution with mean vector 0 and variance covariance matrix sigma square U omega, then the distribution of B is also multivariate normal with mean vector beta, because expectation of B is beta, and variance covariance matrix sigma square U x transpose x inverse x transpose omega x x transpose x inverse. So, now we prove this result. To prove this result, we can write the OLS estimator as B equal to x transpose x inverse x transpose y, then we write y equal to x beta plus u here. So, we get x transpose x inverse x transpose x beta, which is beta, plus x transpose x inverse x transpose u, we get this term. Then we assume that the assumption expectation of u given x equal to 0 still holds. U and x are uncorrelated. So, if we take expectation of B, then expectation of B is equal to beta plus expectation of this second term, which is equal to 0. So, expectation of B is equal to beta for all beta. So, B is still unbiased estimator for beta. So, even if the disturbances are non-spherical, the property of unbiasedness of the OLS estimator B is not lost, it still holds. Then we derive the variance covariance matrix of B. So, to obtain the variance covariance matrix of B, we take B minus beta transpose. So, B minus beta transpose is equal to x transpose x inverse x transpose u into, then we take transpose of this u transpose x transpose is x, then x transpose x inverse. So, we get x transpose x inverse x transpose expectation of u transpose x transpose x inverse, and then we substitute the value of expectation of u transpose, which is equal to sigma square u omega. Sigma square u is a scalar, so you can take sigma square u outside all the matrices. So, you get sigma square u x transpose x inverse x transpose omega x x transpose x inverse. So, we get the variance covariance matrix of B. Further, B is equal to beta plus x transpose x inverse x transpose u, and the distribution of u is normal with mean vector 0 and variance covariance matrix sigma square u omega. So, B is actually a linear function of u, means you can write B equal to beta plus C u, where C is equal to x transpose x inverse x transpose. So, obviously, the distribution of B is also normal and the mean is beta. The variance covariance matrix is C, the variance covariance matrix of u, which is sigma square u omega C transpose. Then you substitute the value of C here, and finally, you obtain the variance covariance matrix of B in this form. So, B is the linear unbiased estimator of beta. B is a linear estimator because you can write B equal to C y, where C is equal to x transpose x inverse x transpose. Then the property of unbiasedness still holds, but the question is B the best linear unbiased estimator of beta? Now, we come to the consistency property of OLS estimator for general linear model. So, if we assume that the probability limit of 1 upon n x transpose omega x is equal to q, and the probability limit of 1 upon n x transpose omega x both are finite positive definite matrices, of course symmetric also, because these matrices are symmetric. So, their probability limits are also symmetric. Then the OLS estimator of B is a consistent estimator of beta. So, the property of consistency of OLS estimator is also not lost. Still, for the model with non-spherical disturbances, the estimator is consistent. To prove the consistency, we write the probability limit of B as beta plus, then you have this term x transpose x inverse x transpose u. You can write this term as 1 upon n x transpose x inverse, then you can take 1 upon n here also. Then the probability limit of this first term is q inverse. So, now you have to obtain the probability limit of 1 upon n x transpose u. So, the probability limit of 1 upon n x transpose u is equal to 0. Actually, this result we have already proved while proving the consistency of OLS estimator for multiple linear regression model under the assumption of spherical disturbances. So, the probability limit of B is equal to beta. Further, if we take the probability limit of variance covariance matrix, means probability limit of expectation of B minus beta transpose, then expectation of B minus beta transpose is equal to sigma square u x transpose x inverse x transpose omega x x transpose x inverse, and then you can write it as, say we divide here by n, and then here again we divide by n, and then 1 upon n x transpose x inverse. So, we get 1 upon n from here, we get n from here, we get n from here. So, we have n square upon n, that is n. So, we must divide sigma square u by n. So, the probability limit is equal to 0. The probability limit of this term is q. So, you get q inverse here, and the probability limit of this term is also a finite matrix. So, say suppose we denote it by R. R is the probability limit of 1 by n x transpose omega x, and then again we get q here. Then we have sigma square u upon n, and then as n tends to infinity, this term tends to 0. All other matrices are finite, q inverse is finite, R is finite, q inverse is again finite, and this term tends to 0. So, this probability limit of variance covariance matrix of B tends to 0. So, this shows that B is a consistent estimator of beta. In probability, B converges to beta, and the variance covariance matrix of B converges to 0. Therefore, B is a consistent estimator of beta. Now, we derive the generalized least squares estimator for beta. In fact, the OLS estimator B is an unbiased estimator. It is a linear unbiased estimator for beta, and then it is a consistent estimator also. But still we have doubt whether OLS estimator is the best linear unbiased estimator or not. So, now we derive the generalized least square estimator. Now, omega is a positive definite matrix. So, you can find a non-singular matrix T such that T omega T transpose is identity matrix, or actually omega is equal to T inverse T transpose inverse, or omega is equal to T transpose T inverse. Now, we pre-multiply the model y equal to x beta plus u by t. So, we get T y equal to T x beta plus T u, and then we write y star equal to T y, x star equal to T x, and u star equal to T u. So, you get the model y star equal to x star beta plus u star. So, basically what we have done? We have transformed this model y equal to x beta plus u to y star equal to x star beta plus u star by pre-multiplying both sides by t. Then we observe that expectation of u star transpose is equal to expectation of u star is equal to T u. So, you get T u here, then we take transpose of this. So, you get u transpose T transpose, and then this is equal to T expectation of u transpose T transpose, and expectation of u transpose is equal to sigma square u omega, and then we take sigma square u outside, we get T omega T transpose, and T omega T transpose is equal to identity matrix. So, you get sigma square u I n here. So, expectation of u star transpose is equal to sigma square u I n, and from here we also observe that T transpose T is equal to omega inverse. So, after taking this transformation, this model 6 satisfies the assumption of spherical disturbance. So, means for this model expectation of u star transpose is equal to sigma square u I n. So, the disturbances are homoscedastic and uncorrelated with each other. Then for obtaining the GLS estimator, we simply apply the OLS procedure to this model. So, for that purpose we minimize S star equal to y star minus x star beta transpose y star minus x star beta, and in fact this is equal to say y star minus x star beta is equal to T y minus T x beta, or you can write it as T y minus x beta. And if you take transpose of this, then you get y minus x beta transpose T transpose. Then from here we obtain T y minus x beta. So, finally, you get y minus x beta transpose omega inverse y minus x beta. So, basically if we apply OLS to this model 6, it is equivalent to minimizing y minus x beta transpose omega inverse y minus x beta with respect to beta. Whereas, in the original OLS estimator for the model with spherical disturbances, we estimate beta by minimizing S equal to y minus x beta transpose y minus x beta. So, this is the difference between OLS estimator and GLS estimator. OLS estimator is obtained by minimizing the residual sum of square S equal to y minus x beta transpose y minus x beta with respect to beta, whereas the GLS estimator is obtained by minimizing S star, which is y minus x beta transpose omega inverse y minus x beta. So, in between you have this matrix omega inverse also. So, we have this result, the GLS estimator of beta is beta hat equal to x transpose omega inverse x transpose omega inverse y. Further, the GLS estimator beta hat is an unbiased estimator of beta. The variance covariance matrix of beta hat is expectation of beta hat minus beta, beta hat minus beta transpose equal to sigma square u x transpose omega x inverse. So, we prove this result. Now, notice that the transformed model 6, which is y star equal to x star beta plus u star. The assumption of spherical disturbances is satisfied, means expectation of u star transpose is equal to sigma square u I n. And then for obtaining the GLS estimator, we have to minimize S star equal to y star minus x star beta transpose y star minus x star beta. That is basically what we have to do, we have to apply OLS to this model 6. This is actually your model 6. So, you have to apply OLS to this model, and when we apply OLS to model 6, we obtain the following estimator of beta, beta hat equal to x star transpose x star inverse x star transpose y star. Now, we write this estimator in terms of x and y. So, we write x star equal to T x and y star equal to T y. So, obviously, x star transpose is equal to x transpose T transpose. So, you get x transpose T x inverse x transpose T y, and then T transpose T is equal to omega inverse. So, we substitute T transpose T equal to omega inverse here, and then we obtain x transpose omega inverse x transpose omega inverse y, which gives you the expression 8 for the GLS estimator. Then for proving the unbiasedness of beta hat, in the expression for GLS estimator, x transpose omega inverse x transpose omega inverse y, we write y equal to x beta plus u. So, this is equal to, you get x transpose omega inverse x transpose omega inverse x beta. So, you obtain beta here plus x transpose omega inverse x transpose omega inverse u. You get this expression, and then we take expectation. So, expectation of beta head is equal to beta plus expectation of this term. Now, expectation of this term is 0 because u is uncorrelated with x and expectation of u is equal to 0. So, expectation of this entire term is 0. So, expectation of beta head is equal to beta for all beta. Therefore, beta head is an unbiased estimator of beta. Then we obtain the variance covariance matrix of beta head. So, you have the variance covariance matrix expectation of beta head minus beta, beta head minus beta transpose equal to, again we write beta head minus beta equal to x transpose omega inverse x inverse x transpose omega inverse u. So, you get x transpose omega inverse x inverse x transpose omega inverse u, then we take transpose of this. So, you get u transpose omega inverse x, x transpose omega inverse x inverse, and then we take expectation. So, we take expectation of u transpose because x is a non-stochastic matrix, or even if it is stochastic, it is uncorrelated with u, and expectation of u transpose is equal to sigma square u omega. So, we get x transpose omega inverse sigma square u omega omega inverse x here, this part, and then this is equal to, you can take sigma square u outside. So, this is omega inverse, then we have omega, again omega inverse x. So, finally, we obtain sigma square u x transpose omega inverse x, and then sigma square u we take outside. So, we have x transpose omega inverse x inverse, x transpose omega inverse x in between, and again we have x transpose omega inverse x inverse. So, we obtain sigma square u x transpose omega inverse x inverse here. So, this is the expression for the variance covariance matrix of GLS estimator. And notice that this expression is different from the variance covariance matrix of OLS estimator. Now, the next result proves the Gauss-Markov theorem for the GLS estimator. So, this is termed as generalized Gauss-Markov theorem. So, suppose lambda is a k cross 1 vector with elements lambda 1, lambda 2, so on lambda k, and lambda transpose beta is equal to lambda 1 beta 1 plus so on plus lambda k beta k. So, this is a linear parametric function of vector of regression coefficients beta. Then lambda transpose beta head is a best linear unbiased estimator of beta, in the sense that it is an unbiased estimator of lambda transpose beta, and for any linear unbiased estimator A transpose y of lambda transpose beta, variance of lambda transpose beta head is less than or equal to variance of A transpose y for all beta. The proof of this result is just similar to the blue property of, or proof of blue property of OLS estimator. We observe that expectation of lambda transpose beta head is equal to lambda transpose expectation of beta head, and then since expectation of beta head is equal to beta, so you get lambda transpose beta for all beta. So, lambda transpose beta head is an unbiased estimator of lambda transpose beta. Further, we write A transpose y equal to A star transpose y star, where A star is equal to T transpose inverse A. So, expectation of A star transpose Y star is equal to A star transpose expectation of Y star is X star beta, and because A star transpose Y star is an unbiased estimator of lambda transpose beta. So, this expectation is equal to lambda transpose beta for all beta, and then this implies that A star transpose X star is equal to lambda transpose. Then variance of A star transpose Y star is equal to sigma square u A star transpose A star, because variance covariance matrix of Y star is sigma square u I n. Further, variance of lambda transpose beta hat is equal to sigma square u lambda transpose X star inverse lambda, and then this is equal to, we substitute lambda transpose equal to A star transpose X star, or lambda equal to X star transpose A star here. So, we obtain sigma square u A star transpose X star transpose X star inverse X star transpose A star, and then we take the difference of two variances. So, variance of A star transpose Y star minus variance of lambda transpose beta hat is equal to sigma square u A star transpose, then in between we have the matrix I n minus X star transpose X star inverse X star transpose A star. Now, this is an idempotent matrix. So, this matrix is positive semi-definite. So, this shows that the variance of A star transpose Y star minus variance of lambda transpose beta hat is greater than or equal to 0. This shows that lambda transpose beta hat has lower variance than any other linear unbiased estimator of lambda transpose beta, or beta hat satisfies the blue property. So, in fact, for the general linear model, it is not the OLS estimator, but the GLS estimator which satisfies the blue property. Then the next result is about the consistency. If probability limit of 1 upon n X star transpose X star is a finite matrix Q star, then beta hat is a consistent estimator of beta, which can be easily proved just like the consistency of OLS estimator. Then maximum likelihood estimation for the general linear model. Say if we assume that U follows a normal distribution, then the maximum likelihood estimator for beta is beta hat ML equal to X transpose omega X X inverse X transpose omega inverse Y, which is same as the GLS estimator. And the maximum likelihood estimator for sigma square is sigma hat square ML equal to 1 by n Y minus X beta hat transpose omega inverse Y minus X beta hat. So, one can easily prove the expression for these maximum likelihood estimators. We have the log likelihood function in the form this, and then we differentiate this log likelihood function with respect to beta. So, we get this expression, we put it equal to 0, we differentiate it with respect to sigma square u, again we put it equal to 0. The proof is actually just parallel to the proof of maximum likelihood estimator for the multiple regression model satisfying its spherical disturbances assumption. Then we solve these two equations, and finally, we obtain these expressions for the ML estimators. So, ML estimator of beta is the same as the GLS estimator beta hat. Further, if you take expectation of ML estimator of sigma hat square, then you get n minus k upon n sigma square u. So, This is a biased estimator and the bias is minus k by n sigma square u. Then in practice actually omega is usually unknown. So, what you have to do? You have to estimate this omega also. Now, suppose omega is a function of q by 1 unknown parameter vector theta. Say for example, in case of AR1 disturbances, this theta is the autoregressive parameter rho for AR1 case. So that we can write omega equivalent to omega theta. And suppose a consistent estimator theta hat of theta is available, then we can estimate omega by omega hat equal to omega theta hat. And then in the expression for GRS estimator, we replace omega by omega hat, and then we get a feasible generalized least square or FGRS estimator of beta as beta curl equal to x transpose omega hat x inverse x transpose omega hat inverse y. So, this is the feasible GLS estimator of beta. When the assumption of spherical disturbances in the multiple linear regression model is not satisfied, it may affect the properties of OLS estimator. In fact, the OLS estimator still remains unbiased as well as consistent, but it is not the best linear unbiased estimator for beta. So, one requires some alternative estimation procedure. So, in this lecture we have discussed another alternative procedure for estimating the regression parameters of the multiple linear regression model when the disturbances are non-spherical, and that procedure is the generalized least square estimator. Actually, this generalized least square estimator is also consistent, it is unbiased also, and it is also the best linear unbiased estimator in the class of all linear unbiased estimators. So, it satisfies the Gauss-Markov property, Gauss-Markov blue property. We have studied the other properties of the GLS estimator also. In next two lectures, I will consider two special cases of the model with non-spherical disturbances, that is the model with heteroscedastic disturbances and the model with autocorrelated disturbances. So, here I am going to stop. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. Today I am going to tell you about the different characteristics of the movement of things around the world that are associated with globalization. We refer to these kind of movements as global flows. Now, the concept of global flows is quite important, and it's important for us to understand the different ways in which these flows might occur. Now, typically when people talk about the movement of things from one place to another in the context of globalization, they're under the misconception that things tend to flow from abroad into the place where they are living. In a very sort of stereotypical manner, there is this idea that with globalization, much of the movement that occurs is from Western countries into non-Western countries. Now, as sociologists, we know that actually global flows are multidirectional. So, which means that as much as there is a movement of flows from Western countries into non-Western countries, there is an equal amount of movement of flows from one non-Western country to another non-Western country, and in fact, a movement of flows from non-Western countries into Western countries as well. Let's take the example of food, for instance. You may be aware of a type of food which originated actually in China and then goes on to Japan, called ramen. For instance, the popular brand Top Ramen that is consumed in India is an example of ramen. Now, ramen, initially the movement is from China, which is a non-Western country, to Japan, which is another non-Western country. From Japan, this very popular food item travels to Western countries such as the US and also more recently to countries in Europe. So there you have a movement from a non-Western country to a Western country. And in fact, now we have very specific types of ramen being consumed in metropolitan centers in India as well. So there's another movement from a Western country to a non-Western country, which is India. So global flows in that sense are multidirectional. A second aspect of global flows is that they could be interconnected. An easy way to think about this would be if you have relatives who are traveling from the US or the UK or Australia, very often you'll see that people request them to carry electronic items with them. They say, oh, can you please get me a laptop, or can you please get me the specific camera lens that I'm looking for. So here you see that the movement of people, which is a person moving from one country to another country, is connected to the movement of technological items as well. So global flows in that sense are interconnected with each other. A third characteristic of global flows is that we could see that they happen in reverse. In fact, they are called reverse global flows. An example of a reverse global flow would be a style of music that you may be very well acquainted with, which is Bhangra. Now, Bhangra music is something that originated, as we know, in the state of Punjab. Now, as you know, Punjab is also a state which has seen a lot of out-migration, not only to other parts of India, but also to other parts of the world. So as people migrated to other parts of the world, they took their music with them. So when people migrated from Punjab to the UK, for instance, they hung on to the music that they were familiar with. So Bhangra moved from little villages in Punjab to the major cities where people from Punjab settled to in the UK. While in the UK, over subsequent generations, this music was transformed. It was not only performed in its original version, but it was also performed with the addition of many different types of beats, which are more familiar to people in the UK. At one point in time, you see that this modified form of Bhangra comes back to India. We're talking about the 1990s, the 2000s. So here you see that that a form of music that originated in India moves out of India to the UK. It is modified a little and then comes back to become extremely popular in India again. So in some ways, this form of music is returning to where it started out, but in a slightly changed manner. We call this kind of movement as a reverse flow.